When you hear about an 8-year-old game platform called Homegames, most developers assume it is a story about fun or graphics engines. But this project has quietly become something far more critical, an accidental engineering stress test that exposes why consumer-grade GPUs fail at real-time AI inference. The gap between code running in a notebook and systems working smoothly on your local server often comes down to one misunderstood trade-off. If you do not understand how hardware constraints shape your ability to run agents, you will waste months building architectures that choke under latency or drain your electricity bill without delivering usable performance. The core of the problem lies in what we call the gaming GPU fallacy. For years, developers have assumed that a high-end graphics card like an RTX 3060 or even a flagship 4090 is the universal key to local AI deployment because it has massive raw compute power. However, consumer hardware is optimized for rendering polygons and handling bursty graphical loads, not for the continuous, sustained pressure of processing tokens in real time. This design mismatch means that generic gaming rigs often consume between 150 and 400 watts just to sustain idle or low-load AI tasks. In contrast, dedicated appliances designed specifically for inference can operate at roughly 20 watts while delivering comparable utility. This massive power disparity creates inevitable thermal throttling and noise issues that make high-end gaming PCs unsuitable for always-on agents in a home environment where silence and efficiency matter more than peak theoretical speed. This inefficiency is compounded by the reality of memory bandwidth, which remains the primary bottleneck rather than raw compute speed. While 8 gigabytes of video RAM was once considered sufficient for early models, modern context-length overheads have rendered it largely inadequate. The specific issue here involves what engineers call the KV cache, a data structure that grows linearly with conversation history to maintain state during inference. As your agent interacts over longer periods or processes multimodal inputs, this cache consumes memory rapidly. A standard gaming GPU with 12 to 24 gigabytes of VRAM often hits a hard wall when handling these expanding contexts. When the system runs out of fast video RAM, it is forced to swap data into slower CPU memory, which instantly kills latency performance and makes real-time interaction feel broken or unresponsive. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. The situation becomes even more complex when we consider the energy dynamics of iterative AI agents. Running a single inference task is relatively straightforward, but an agent that uses tools, reasons through steps, and loops back to correct itself creates what researchers call an agent energy spike. Data from recent studies indicates that without specific efficiency supervisors built into your architecture, local agents can waste between 15 and 20% of their compute power on failed trajectories before the system even realizes it is stuck in a loop. This means you are burning through electricity and generating heat for computations that lead nowhere, further exacerbating thermal throttling issues on hardware not designed to handle these erratic workloads efficiently. This brings us to why unified memory architectures often outperform discrete gaming GPUs for many home-based AI workloads. Silicon with integrated high-bandwidth memory, such as the Apple M-series chips used in Mac Minis, offers a distinct advantage due to its ability to share memory between CPU and GPU without the latency penalties of PCIe transfers. A Mac Mini equipped with an M4 Pro chip can run 7 billion parameter models at approximately 30 tokens per second, while handling larger quantized models up to 70 billion parameters more efficiently than a noisy, power-hungry gaming PC with similar raw floating-point operations. The lesson here is that speed for local AI is not just about how many calculations you can perform. It is fundamentally about memory bandwidth and thermal stability required for always-on tasks where consistency trumps peak bursts of performance. The 8-year evolution of the Homegames project serves as a perfect case study to tie these concepts together. As the platform shifted from simple text generation to complex real-time agent interactions, the underlying hardware constraints became the limiting factor rather than the software logic itself. The timeline mirrors the industry-wide realization that you cannot treat an LLM inference engine like a game loop without accounting for memory bandwidth and thermal limits. Developers often blame their code when systems fail locally, but this project demonstrates that if your local inference is too slow or unstable, the problem is frequently not better algorithms. It is almost always a mismatch between the silicon architecture and the specific workload of an iterative agent versus a static rendering engine. Understanding these trade-offs has become a core competency for any serious AI practitioner today. Knowing why your local server fails allows you to make informed system design decisions that avoid the common trap where code works perfectly on a developer machine but collapses under real-world deployment conditions. You must select hardware based on memory bandwidth and power efficiency rather than marketing metrics like total operations per second or raw CUDA core counts. This judgment applies whether you are building a personal assistant, an automated coding agent, or a voice interface that needs to respond instantly without lag. By recognizing that high-end gaming GPUs are often the wrong tool for these specific, always-on AI tasks due to their power and noise profiles, developers can avoid wasting hundreds of dollars on upgrades that do not solve the fundamental latency issues inherent in their architecture choices. The statistical reality is stark. When teams ignore these hardware constraints, they face a significantly increased likelihood of operational failure compared to those who designed for memory efficiency first. The cost of ignoring this engineering judgment extends beyond broken code. It manifests as wasted compute cycles and reduced earnings from systems that simply cannot sustain the required throughput over time. In environments where reliability is paramount, failing to account for these physical limitations can lead to a reduction in effective performance by double-digit percentages during critical operations. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.